So, what does it really mean to be certain about something? In day-to-day life, you might be certain it's going to rain or that your team's going to win. But in math, certainty is a whole different beast. It means having a proof, an argument that's so rock solid, so absolutely airtight, there's just no room for doubt. But what happens when the very idea of a proof starts to fall apart? What if the foundations of certainty itself start to crack? Well, today we're diving headfirst into the incredible story of proof theory. It's a quest to understand the very structure of truth and logic itself.
Okay, so here's the game plan for our journey. First, we're going to look at a crisis that pretty much shook mathematics to its core. Then we'll meet the genius who completely reshaped logic. After that, we'll uncover the holy grail of proofs. And then, and this is super cool, we'll see how all this abstract theory actually powers our computers. And we'll wrap it all up by asking what any of this means for the very definition of truth. Sounds good? All right, let's jump right in with the crisis that kicked this whole thing off.
All right, so let's set the scene. We're in the early 20th century, and for all intents and purposes, mathematics feels like it's built on solid granite. I mean, it's the most certain thing we have, right? But deep down in the very foundations, some serious cracks are starting to appear. And this was the question that was absolutely terrifying mathematicians, keeping them up at night. People were discovering these bizarre paradoxes in set theory. And you gotta understand, set theory was supposed to be the bedrock of all of math. It was like a physicist finding out that gravity sometimes just stops working. It hinted that the whole system, the entire beautiful structure of mathematics, could have a hidden contradiction, like a logical time bomb just waiting to go off and bring everything crashing down. The hunt for absolute certainty was officially on. So, in steps the great mathematician David Hilbert. And in response to this crisis, he launches this unbelievably ambitious plan, Hilbert's program. His idea was, well, it was breathtaking. He thought, what if we could treat mathematical proofs themselves as things we can study? He imagined a proof theory, a way to analyze every possible proof and show once and for all that math was consistent and safe. Just wow. But just as this massive project was getting started, a logician named Kurt Gödel comes along and delivers a major gut punch. His work basically proved Hilbert's original dream was impossible, forcing the entire field to rethink everything and find a whole new way forward. So where do you go from there? Well, that new path was carved out by a truly brilliant logician named Gerhard Gentzen. This is in the 1930s, right in the shadow of Gödel's earth-shattering results. And Gentzen, he doesn't try to patch up the old broken system. No. He invents a completely new, revolutionary way of even thinking about what a proof is. And this, right here, was the core of his genius insight. See, up until then, pretty much everyone saw proofs as a straight line. You start with your axioms, the supposedly self-evident truths, and then you just take one logical step after another until you hit your conclusion. Simple, right? The problem was, this made it almost impossible to see the big picture, the overall structure of the argument. Genson's idea was to flip that on its head. He said, what if we think of a proof not as a chain, but as a tree? A tree that branches out from the final conclusion all the way back to its most basic assumptions. And that structural view changed absolutely everything.
And this comparison really shows you everything. The old way, the axiomatic systems, it's just this long, rigid, linear march. But Genson's approach, it's completely different. He basically said, forget about memorizing a huge pile of axioms. Let's focus on a few simple rules for how we actually use logical words like and, or, and if. He shifted the entire focus away from these static truths and onto the dynamic structure of our reasoning. And this one little change suddenly made proofs totally transparent and analyzable in a way they had never, ever been before.
So Genson's first brilliant creation was something called natural deduction. And honestly, the name says it all. It was literally designed to mirror the natural way that we humans actually reason. For instance, the and introduction rule is just, well, it's just common sense. It says if you've proved A is true and you've proved B is true, then guess what? You're allowed to conclude A and B is true. That's it. It's so intuitive, so elegant, and it puts all the focus right where it should be, on what the logical words themselves actually mean. His next invention, though, the sequent calculus, was even more powerful. Now, okay, this one's a little more abstract, so bear with me. But the key idea, the really beautiful part, was that he created a system with perfect symmetry. The rules for making assumptions were a perfect mirror image of the rules for drawing conclusions. It's this elegant, balanced structure that turned out to be the master key that would unlock his next massive breakthrough.
You know, every great quest has a holy grail, right? For Gentzen, and really for all of proof theory, that grail was getting rid of one specific, pesky rule of inference, a rule known simply as cut. So what on earth is this cut rule? The easiest way to think about it is like a shortcut or a lemma. You know how in a math argument you might say, and because of this other theorem we already proved, we know this next step is true? That's a cut. You're taking a shortcut. And look, they're super useful for making proofs shorter, but for analyzing a proof, they're a total disaster because they hide all the real logical steps. You're just pulling in this big chunk of outside information, and it completely obscures the direct path from your starting assumptions to your final conclusion.
Yeah, think of it just like this. A proof with a cut is like following a GPS that takes you on a bunch of weird back roads and shortcuts. A cut-free proof, though, that's the direct, step-by-step route. Gentzen's monumental, almost impossible task was to prove that you could always get rid of the shortcuts, that you could take any proof, no matter how complex, and mechanically unfold every single lemma, replacing each one with its own full proof until you were left with one long, continuous, completely direct argument from beginning to end. And he did it. He actually did it. This is the cut-elimination theorem, and it's honestly one of the most profound and beautiful results in all of logic. The consequence is just staggering. It proves that logic doesn't need any clever tricks or fancy shortcuts to work. Anything that is provable can be proven directly, from the ground up. This means logic is totally self-contained. You can't secretly prove a contradiction by using some clever shortcut, because if you could, his theorem guarantees you could also prove it directly, which we know is impossible. In a way, it was the guarantee of consistency that Hilbert had been dreaming of, at least for the world of pure logic. Okay, so for decades, proof theory was seen as this super abstract, deeply philosophical corner of math. Interesting, sure, but practical? Not so much. But then, it collided with the dawn of the computer age, and the results were nothing short of revolutionary. All right, seriously, this is where the story takes a wild turn. Decades after Gentzen, logicians and computer scientists noticed something absolutely mind-blowing. The tree-like structure of one of Gentzen's proofs, it looked exactly like the structure of a computer program. And I don't mean it was just similar. It was a perfect one-to-one correspondence. A proof, it turns out, literally is a program. And a computer program is a proof. They are the same thing. And just look at how literal this translation is. It's incredible. A logical proposition, like A, is just a data type in a program. A proof that A implies B isn't like a function that takes a thing of type A and gives you a thing of type B. It is one. And get this, remember cut elimination, that whole process of getting rid of the shortcuts in a proof? In programming, that's literally just running your code. It's the process of computation itself, simplifying the program down to a final answer. And this is way more than just a cool philosophical party trick. This correspondence is the rock-solid foundation for a huge chunk of modern computer science. It's the reason why certain programming languages are so incredibly robust and reliable. Their type systems are secretly logical proof checkers. It's the magic that powers proof assistance, software that can formally verify that an airplane's flight control system is mathematically bug-free or that a complex new math theorem is actually correct. This wild, abstract theory from the 1930s is running under the hood of some of the most critical technology we use every single day. So we've seen the history, we've seen the wild, practical applications. But for this last part, let's circle back to those deep philosophical questions that got this whole thing started. What does proof theory really tell us about the nature of truth? This quote here really gets to the heart of a very weird problem. In classical logic, a sentence like, "If my dog can play the piano, then the sky is blue," is technically considered a true statement, just because the second part, "the sky is blue," is true. But that feels weird, right? There's no connection. Proof theory offers a different way of looking at it. It suggests that for an if-then statement to be meaningful, there has to be a real, genuine connection, a proof, a path, from the if part to the then part. And this leads to a pretty radical idea called proof-theoretic semantics. It basically says that the meaning of a logical word like and or isn't something you find in a truth table. No, its meaning is the rules for how you use it. The meaning of the word and is the rule that says if you can prove A and you can prove B, then you can put them together and claim A and B. Meaning isn't about how things match up with the outside world. Meaning is built from the very rules of our reasoning. And so that leaves us with this final, really deep question to chew on. Is truth something we just discover? Something that's out there in the world waiting for us to find it? Or is truth something we construct? Something that only exists because we can build a rigorous, step-by-step justification for it using the rules of our own logic? It really makes you wonder, is the certainty we're all searching for something we find? Or is it something we have to build for ourselves, one logical step at a time?